Today specifically we're talking more about the next learning target. It's probably I guess 8.2 if you're following the numbers a little bit. That's probably a little combination actually of both, A1 and A2. We're still working with just some basic vectors. We're not doing a ton of application yet. But specifically, our learning target today is I can find the resultant of two or more vectors. Okay? And really what that means is what's going to happen to something when more than one force is acting on it at the same time. Okay? Yeah. It'll go in a third direction. You know, we kind of talked a little bit about it. If two people were pushing on that chair, potentially, if we had somebody pushing on the chair headed to the west, and somebody's pushing on the chair headed a little bit to the north, depending on how much force they're pushing, okay, the chair is not going to go directly north, it's not going to go directly west, it's going to go somewhere in between, okay, kind of a third direction. Okay, that will be the resultant force. So, the word resultant, when you see that, okay, resultant is what we call the sum of two or more vectors. Okay. In terms of vectors, it's the sum of two or more vectors. Okay, it's what happens when two or more forces are acting on an object. It's the result. It's what happens to that object when all those forces are acting on it. Okay? Kind of make some sense? Okay? This can apply to a lot of different things. It definitely, when you have airplanes trying to go a certain direction and you got wind pushing it one way, you got to be able to adjust. You got to adjust your direction so you can go where you want to go because of those two forces. The plane's trying to do something, the wind's doing something. You want the plane to go a certain direction, so you got to make sure you put it at the right angle. Okay, you try to canoe across the Mississippi River, okay, or kayak across it. All right, if you want to go straight across the Mississippi, you probably don't want to aim straight across, because what's going to happen? You're going to get pushed downstream a little ways. Okay, so we're talking about two or more forces acting on an object. You got your kayak force trying to go straight ahead, but you got the current force doing something to it too. So the result is going to be what happens when you put those two forces together. So I like the story problem part of this a lot more than the math because it's a little more applicable. All right, but I want to give you some basics to get started. Okay, we will start though with the simple story problem. Okay, I'll go kind of to a river a little bit. All right, let's say you can swim at a rate of 5 miles per hour, okay, and you're going to try and go due west. When I say due west, it means exactly straight west, okay? Okay, so you're going to try and swim 5 miles per hour straight west, but you're doing this in a river, and the current in that river is going to push you 2 miles per hour, and we'll just say, because most rivers flow due south. Okay, in the northern hemisphere. Okay, so you're going to try to swim due west while a current is pushing you 2 miles per hour due south. I want to find the resultant both magnitude and direction. So now I want to know, okay, well, how fast did you actually end up swimming, and in what direction did you travel? That's the two things we're trying to figure out here. Okay? Got an idea what's going on? What do you think we should do? Draw both of them. Yeah. Okay. If you want to get real fancy, all right, so, yeah, I know. That's crazy, right? Okay, that's my river. Okay. I'm trying to swim due west, so I might say I'm starting here on the east side of the river, all right, and I'm going to try to do that at 5 miles per hour. while the river is doing what?
Downstream,
Pushing
2 miles per
downstream 2 miles per hour. Where do you think I'm going to draw that vector?
From the end of the other one.
Yeah, from the end. They call it the tip to tail method, okay? So I'm going to draw this vector, and from the edge of that one, that's where I'm going to draw my new vector, okay? Or the other vector that you're adding to it, or the other force that's going on, okay? And it doesn't need to be to scale, just make sure you label it to scale, okay? So I'm trying to do this. I'm trying to swim 5 miles per hour due west while the current is doing this. So what do you think is the result of those two forces? Jake?
The hypotenuse.
Yep. You started here. You tried to do this while the current was doing this. So what actually ended up happening? Right there. You actually ended up going a little bit diagonal. Let me get a different color out here so I can show you. Red. That red arrow is our resultant because that is the actual path that you ended up swimming. If you tried to go straight west while a current was pushing you south, here is the path that you actually took. Logical? Make sense? I want to know the resultant's magnitude and direction. Well, is this any different than what we have been doing? Not really. Where do you kind of want to draw your x and y axes?
right at the where you started.
Starting point. Yep, absolutely. So kind of do one of these numbers right there. Okay? So, I'm not, but this is 0 degrees over here, right? This would be 90, 180, 270. So our answer is going to be, direction answer is going to be somewhere between 180 and 270, right? Okay. But we want both magnitude and direction. Magnitude is what? Distance or length of the arrow. Okay. How are we going to get the length of the arrow? Pythagorean theorem. So 5 squared, 25, 2 squared, 4, 25, 4, 29. That's the square root of 29. Somebody has a decimal, please.
5.4.
5.4, that's to the nearest tenth?
Yep.
Okay. So, about 5.4 miles per hour. We did Pythagorean's theorem for that. Okay. To find our direction, what am I going to want to find in this picture?
Inverse tangent.
Yeah.
Correct, that's what I'm going to do, but what do I want to find?
That angle between the resultant and
Right there, yep. Good, guys. Okay, that angle right there. And Derek said it, the inverse tangent of 2 over 5, okay, would give us that angle right there,
21.8.
21.8, okay?
South and west.
So we could say the resultant would be swimming 5.4 miles per hour at what?
21.8 degrees south of west.
I like it, 21.8 degrees south of west. Okay? So 5.4 miles per hour at 21.8 degrees south of west. What other degree could you say if I want to go all the way?
201.8.
201.8 degrees. Then do you have to put any label on it? Nope. Okay? So thoughts on that? Yes, Austin.
Why do you use the inverse?
To find an angle.
Use inverse tangent.
Because wouldn't the tangent of theta equal opposite over adjacent, 2 over 5?
Yeah.
So how do you find out what theta is?
Oh, inverse.
You do inverse. You do inverse tangent.
Oh, okay.
You inverse tangent both sides to get theta by itself.
Okay.
Remember to find angles, so.
Do you have to use tan?
Well, you don't have to, but
It's easier.
why would you want to use something different?
Sounds easier.
Sine is easier.
You'd have to use the exact number.
You'd have to use that really long decimal, but yeah, that's fine. You'll get the same answer, but
Can you just use like square root of 29?
yes. Yeah, that would probably be quicker than using the whole decimal. Yeah. Why is sign easier?
Just opposite of it. It's the first one we learned stuff.
Gotcha, just because it's the first one? Okay, no, it's fine, I'm just asking, so, it's interesting.
Can't you say like 68.2 degrees west of south?
68.2 degrees west of south, yes, that would work too. That would be a third way to write it, absolutely. So, that's kind of the idea of resultant, is you're trying to figure out what happens when two or more vectors are added together or put together. Okay? We could do this with ordered pairs as well. Okay? And some of you will end up doing more of the complicated story problems with ordered pairs because you're not a huge fan of law of sines and cosines, is what it's going to come down to. Okay? I like drawing pictures myself, but I'll show you both. Physics is usually done a lot more with the components, x and y components, for sure. Okay, but you can do it with pictures too. In this situation, that vector that represented what we were trying to do when we were swimming due west. Okay? How could I represent that vector using an ordered pair, x comma y?
5 comma 0.
Almost.
0.5. Negative, or negative 5.
Negative 5
Or yeah, negative
comma
5.
0. Because if this is my x and y axis right here, and I got a vector going straight that direction, 5 units, I would say that vector goes negative 5 in the x direction and 0 in the y direction. So that vector would be negative 5 comma 0. This would represent the swimming vector, right? What is the current
0, negative 2.
vector?
Negative 5.
It'd be negative 5, negative
Just the current.
That'd be 0,
2. Well, you start at
negative
negative 5. How do you-
No, I'm completely separating myself. I'm thinking of each vector individually. You guys are already resulting them, basically. But the current by itself is simply this, right? Which would be what? 0, negative 2, right? Because it's going 0 in the x direction, but it's going negative 2 in the y direction. Okay? Well, remember the very first definition I gave you that said the resultant is the sum, adding, of two vectors, two or more vectors. So if I take negative 5, 0, plus 0, negative 2, take a wild guess on what you get.
Negative 5, negative 2.
Negative 5 plus 0 is negative 5. 0 plus negative 2 is negative 2. So your resultant vector would be negative 5, negative 2. Okay? That would be your resultant vector written as an ordered pair. Okay, that would be your resultant vector written as an ordered pair. To find the magnitude and direction, x squared plus y squared equals r squared, Pythagorean theorem. To find the, I meant magnitude if I said direction, I apologize. To find the magnitude, negative 5 squared plus negative 2 squared equals r squared. Okay, to find the direction, inverse tangent the y over x. Okay, so most of you are probably thinking, well, that seems a little bit different. The picture maybe makes more sense and is easier, I'm guessing, but when you start having not right triangles anymore, then sometimes the component method becomes much simpler. Or especially when you start to have 3 different forces acting on the same object at the same time, then the picture can get really crazy. You'll have multiple triangles you got to try and solve. It's a lot easier sometimes to just find the x and y values and add them all together.
How would you do 3 forces?
Picture-wise,
Yeah. I mean, just like A-wise, like. if they're-
Find the x and y components of each vector by itself,
Oh, okay.
and then add all the x's together of them, add all the y's together of them, get your answer as an ordered pair, and then find the magnitude and direction of your answer. Okay? That's probably the way you'll go when you start getting three of them. Okay? Couple other operations here, couple other examples. Let's say I tell you that vector b is 4, -3. Vector c is 2, 7. We essentially have already done this one. But find vector A if vector A is equal to vector B plus vector C. It is as simple as you think.
So 6, 4.
6, 4. If you're going to add the two vectors together, okay, this vector is saying you're going 4 units in the x direction, but you're adding this vector to it, well that vector is going 2 units in the x direction, so the sum, if those two forces act together, if these are my two forces that are acting together, then vector A will equal whatever the x values are added together plus whatever the y values are added together. So in other words, vector A in that case would be 6, 4, like you guys said. Okay? How about we haven't really talked about subtracting a vector, but let me give you a little idea what subtracting a vector is. Okay? I'll come back and I'll use the chair. Okay? Let's say some vector or some force is pushing on the chair at 10 pounds of force in a certain direction. Okay? So if this represents the initial force, if I wanted to subtract that force, you're not really subtracting it, you're just adding its opposite. Because isn't subtraction the same as adding a negative? And that was when you first were taught integers. If you didn't like minus something, you could say plus the opposite. Okay? So what is the opposite of a 10-pound force that direction?
Negative 10 pounds.
A 10-pound force in the opposite direction. Okay? That's all that it is. Okay? You're just adding the opposite of it. And by opposite, it just means complete 180 direction-wise. Okay? An opposite force or an opposite vector is just exactly the same force, just in the complete 180-degree difference as far as direction is concerned. Okay? Well, what is the complete opposite of this vector? Well, the opposite of going 4 in the x and -3 in the y would be going -4 in the x and +3 in the y. Okay, that is the complete opposite direction. So if I said A is the result of taking vector C plus the opposite of vector B, well, you can just subtract. Take the C, 2, minus the 4, 7 minus the -3. 10. So answer?
2,
2, comma negative 10.
2, 10. You just said
-2, right?
Yeah.
yeah.
Because aren't we taking 2 minus 4, or 2 plus the opposite of 4? So -2, comma 10. All right?
So if it was the vector A equals vector B minus vector C, you would take the opposite of C?
If it said B minus C, I'd take the B value plus the opposite of the C value, or subtract the C value. So yeah, if it was the other way around, it would be to negative 10. Which would make sense if you do it the other way around, you'd get the exact opposite of this, because in math, I mean, if you think about it, what's 10 minus 7? 3. What's 7 minus 10? Just the exact opposite, right? Okay. So, one last thing, scalar multiplication, go along with those same thing. If I said, let vector A equal 3 times vector C, all that means is you've essentially draw vector C 3 straight times, or in other words, it's 3 times as long. The resultant would be, that'd be like adding C plus C plus C, okay? Or you really can just, instead of adding it 3 times, take it and multiply it by 3. I can't remember what was C, 2, 7. So what would 3 times C be?
621.
621. How would this compare to vector C
3 times.
as far as magnitude and direction?
Same direction.
Same direction, exactly the same direction,
But just longer.
but 3 times as long, 3 times as much force. It'd be like basically saying, okay, you're pushing this way, but now all of a sudden you're pushing 3 times harder than you were originally. To change it back to some physics a little bit. Okay? So, for the most part, these problems stay pretty basic, but we're setting you up to really work on story problems next week. Okay? I enjoy the story problems quite a bit. They will help you in physics, I'm sure. Those of you that have taken physics probably are starting to recognize a little bit of correlation here. But page 490, 13 and 38, and page 497, 23 through 33 odd, 44, 45, 47.